All right, last week of the third 9 weeks. By the way, you guys, listen. You guys know, for you seniors, which is I think all of you, your class rank locks at the end of this 9 weeks. You still have to get credit to graduate, so you can't like completely shut it down. I mean, you can put it in coast maybe, but you still got to pass. So your class rank locks, but you still have to pass everything. You still have to send a final transcript to your colleges, that sort of thing. So, does the grades end on the 11th? And the answer is kind of. For class rank, yes, but for everything else, no. So don't shut it down after this week. Speaking of things ending, because class rank locks, everything has to be in by the 11th. Like there are no incompletes this 9 weeks. Everything has to be in. Yeah, so you got to have everything turned in by Friday, just to be clear. I tweaked this week by a little bit because we've already done area under the curve. Today we'll do area between curves, volume by cross section tomorrow, volume by disc and washer on block day. Some years we do these together, so it's okay we're kind of spreading them out this year. Then spring break, of course. Yay. Then when we come back, L'Hôpital's rule, which is a very easy and very helpful rule to learn. And then review. And then we'll test on the block day we return. And that's the end of the new material. Like, that's it for Calculus AB. Then we start AP review. And we'll do that for 6 weeks or so. So we'll try to recover everything starting on Friday, whatever that day is, 25th. So kind of see what's up ahead. So no more tests this 9 weeks. I hope that's good news for you. Maybe you have tests in other classes you can worry about, but not in here. Although do keep up, because you don't want to just put it all off and try to learn it the Tuesday before the test after spring break. All right, you've got the worksheets, notes / worksheet for today. Area between two curves classwork, and I just went ahead and ran off both of them together. Area between two curves homework. So the first page is notes that we'll do together, and the second page will be your assignment. All right, a lot of this we kind of know, so hopefully this isn't too much of an extension. Guess we'll find out. Consider two functions f and g that are continuous on a to b. If the graphs of both functions are above the x-axis and f is greater than g, you can find the area between the two graphs as the area under the graph of g subtracted from the area under f. Picture below left. So that's this first picture here. So we know that the area under f, like when we say area under the curve, we mean all the way down to the x-axis. So that red area would be the integral of f. All right, that'd be all of that. If we integrated g, it would be the blue area. Integral of g. And so this is like, you did this in geometry. A couple days is usually what we spend on it. Like, you find the area of the big circle and you subtract out the missing square. You remember that long ago? That was pretty easy, but it gets you started on thinking, and this is sort of the end game of that. The integral of f is the whole area. The integral of g is the bottom part. And so f minus g is the area we'd be looking for. Back to reading the notes here. The area of a represented rectangle is width times height. All right, so this is sort of back to explaining how to do area. We're not really worried about this. The base is delta x. The height of each rectangle is f minus g. F minus g, top minus bottom. And as delta x goes to 0, so as we shrink the width of the rectangle, right? Our estimate gets better. This is a Riemann sum. If we just do, this is the Riemann sum. Top minus bottom, that's the height of the rectangle. Delta x is the width of the rectangle. And so we add up all the rectangles. But what this is saying, as x goes to 0, so if our width gets smaller and smaller and smaller, the accuracy of this area gets better and better. And we end with the integral of, it's almost better to remember top minus bottom, because we'll use that a lot. Top minus bottom. Otherwise you end up with a negative if you do it the other way around. Emily.
What does it say on top of that? The net equation?
Right here?
Yeah.
Height and width, sorry.
No problem.
So conclusion is the area of the shaded region is the top one minus the bottom one. Like this is just the whole area minus the missing area. Now, suppose the curves are not both above the x-axis. So this one it's a little bit easier because they're both above the x-axis. When they're not above the x-axis, it feels a little bit weird, like, wait, is this still going to work? I'm not going to do the last one, but we'll do this first one. So the red area would be integral of f of x dx. The blue area, well, if we want the area, we would need to put a negative on that. Right? Because if we integrate that, we're going to get a negative number because it's below the axis. So we would put a negative on there to fix it. And this time, if we want the total area, we need to add the red and the blue. So if we add the red and the blue, we get f of x plus negative g of x. And you end up with the same thing, f minus g. So it feels different, but it's the same result. It's always the top minus the bottom. In fact, if you look at the last one, forget about all the negatives that we could get confused with here. It's always top minus bottom from A to B dx. So if I just do the integral from A to B of g of x, it's going to give me a negative number because it's below the axis. But I don't want it to be negative. I want to count it as area. So I put a negative on there, not to make the answer negative, but to make the answer positive. So if I want to add those two areas, the red area plus the blue area, but the blue area has a negative sign on it, and a negative sign in order to make it positive. Again, you don't really need to worry about that. It's always the top one minus the bottom one, regardless of where they're at. So the pictures are trying to get you to understand some concept stuff, but it's always just top minus bottom, because that'll be the height of those rectangles. Also thinking top minus bottom will help us when we get to some more problems later that are a little bit trickier. All right, as we go through the problems in this section, we will use extensively the calculator's ability to find numerical integrals. Basically, we're going to let the calculator do a lot of the work. We're going to focus on getting it set up, and then we'll let the calculator take it from there. We will not go through the fundamental theorem of calculus. That's where you integrate by hand, plug in the top, plug in the bottom. That's the fundamental theorem of calculus. That's what your calculator is going to do. So, I don't know, maybe this is a little misleading. We're not going to do that, but the calculator is going to do that. We'll let the calculator do it for us. On the AP test, you're allowed to use the calculator's ability to numerically integrate as long as you show the proper setup. example 1. Find the region bounded by the graphs. One's a parabola, one's a line, x equals 0, and x equals 1. First, sketch it. Well, sketching it is provided on this one, but it's not like a trivial thing because you got to get the top one correct. You have to know which one is the top one. So in order to put these in the calculator, I'm going to call these y1 and y2. Zoom in a little bit, might help. Okay, I'm writing really small. And I need to figure out which one's top, because I need to do top minus bottom. Now on this one, I hope you know which one is the top one and which one is the bottom one, just by looking. Do you know which one is the top one? And why? How do you know which one is the top one? Right, the y1's a parabola. Only one of those is a parabola, so that's y1. I don't have to worry about that one. The bottom one's a line, slope -1. That one's y2. Now, more generally speaking, you might need to put them in the calculator. If they're both like weird functions and you don't know what they look like, then you put them in to see what they look like. And you might even need to, if you take your cursor and go over to the left, you can change sort of the font or the boldness of the graph. That way you'll know which one's which. I'm going to make my window match the window that's here. 0 to 2 and -3 to 9. The scale doesn't really matter, but I'm going to make it match. Really make it match the picture on the. So now it's clear that you were right. Of course you were right. This wasn't a hard one. The parabola is the top one. The line is the bottom one. So the integral is, well, it's said from 0 to 1. So from 0 to 1. I'm going to show a lot of work on this one. It's always top minus bottom. Otherwise, you're going to get a negative answer. Which means that sometimes, not always, don't do this because it doesn't always work. But if you do the integral and you get a negative answer, there's a decent chance that you just got the top and the bottom wrong, and all you need to do is change the sign of your answer. It's not guaranteed to work every time, but if it's a simple one and you switch top and bottom, you'll be off by a negative sign. Let's see, so from 0 to 1, the top one is y1, the bottom one's y2. So rather than rewrite the whole function again, I'm just going to write y1 minus y2. That is acceptable showing your work for the AP test, because as long as you relabeled these y1 and y2. So you don't have to rewrite the whole thing, the whole equation for each of them. You could just say y1 and y2. Then getting your calculator to do that. Let's see, second calc. I want to calculate some stuff. We'd like to do an integral. Whoops, that's not what I want. Where is it? That's usually where it is, I thought. Nope, there it is. I want... Alright, second calc is when you want to do something on the graph. Those are graph buttons. I don't want to see this on the graph. So go to math. And then option number 9, I don't know why some of those are marked out on this calculator, but we don't need those. Option 9 is function integration. And if you have a reasonably updated operating system on your calculator, it looks like that. I don't know if we still have any old ones that don't look like that. So we're going to go 0 to 1. Here's the best part. You don't have to type in x squared plus x plus 2 minus negative x. You can do y1 minus y2. So those are variables. So you go to vars. And those are y variables. It's a function. And you want to do y1 minus vars, y vars, y2 dx. So Math 9 gets you the integral, and then vars gets you y1 and y2, assuming you've put them in for y1 and y2, which you probably have to look at the graph. And then your calculator thinks for a little bit, and it gives you the answer. So computation for this unit is minimal, because your calculator is going to do all the computation. This unit is all about understanding the concept of setting it up and knowing all the buttons on the calculator. So the area we just found, yeah, we should shade that in, is 3.33323. Example 2. Find the region bounded by the graphs y equals 6 minus x squared and y equals x. Again, one's a parabola, one's a line, so this one's easy to pick out who's who. It doesn't matter which one you call which. Just be careful to keep it straight when you go to your calculator. So y1's the parabola, y2's the line. Regions bounded by the graphs. So it's the integral of y1 minus y2. But what are the limits? How do I know from where to where? Well, it wants bounded by those two curves, so it's not negative 4 to 4. It's wherever those intersections are. Well, what would be a really good tool to tell me where they intersect? The calculator. Calc intersect. Although make sure you put in y1 and y2 correctly. Minus x squared for y1 and just x for y2. I really don't need the one to be bold and one not to be bold, but nothing wrong with leaving it like that. Negative 5 to 5. I'm going to do negative 5 to 5 on both. I can't see the top of the parabola, but that's fine because all I really want are those intersections. Second, calc intersect. And then it walks you through. First curve. Well, first curve is y1, so enter. Second curve, y2, enter. Guess. Well, then I need to move my cursor closer to one of the intersections. And that intersection is at negative 3, 3. So that's my lower limit is negative 3. And then I need to do the same thing for the other intersection. Second calc intersect. First curve, second curve. It does those automatically as long as you only have two curves in there. But then guess, so go closer to the other intersection. That's a 2, 2. So we'll integrate from negative 3 to 2 of y1 minus y2. Why don't you see if you can hit all the right buttons to get the answer for that one? So 20.833. Always round to 3 decimals. And showing the integral is showing your work. So don't just give me the answer, but once you write the integral, that's showing your work because you know the calculator can do that. We can skip example 3. It's pretty similar to what we just did. Example 4 is a little bit something different in there. Find the region bounded by y equals 2x cubed and y equals something with an x squared. So again, I'm going to label them y1 and y2 so I can put them in my calculator. One's cubic, one's parabolic, so again, it's not hard to figure out who's who on this one. So y1 is there's the cubic graph. And we'll make y2 the red one, the parabola. Find the intersections. The middle one's at x equals 0. That one's probably at x equals 3, but I don't know. Let's let the calculator figure this out. So 2x cubed minus x squared minus 14x, 4x minus x squared. Please make sure you label them y1 and y2 on the paper when we give it to you. That way when you use those the rest of the time, I'll know what you're talking about. Alright, those graphs don't look the same because my scales aren't the same. My window isn't the same. I don't have to match them exactly, but the closer you make them match, the better your graph looks, or the more like the paper it looks. All right, second calc intersect. First curve, second curve. There's only 2 curves, so just enter. Guess. X equals negative 3. I'm guessing the other one's positive 3, but you better not assume that. Like, as our first time through, they're giving us problems that have nice intersections. That won't always be the case. Sure enough, x equals 3. All right, the integral is, okay, this one's different. This one's tricky because we have to do top minus bottom. Which one's the top one? That's a trick question. Which one is the top function? There isn't a top one. That's a fair answer. That's a fair answer. You're right. Something's tricky going on here.
For that, doesn't it have to be the red one as the top one?
So you guys are looking at the right thing. It's like, well, over here the top one is red. Over here the top one's blue. Maybe we should have kind of shaded in the area we're looking for. Maybe that would help us.
Yeah.
We've got to do 2 integrals because there's a different top and a bottom. And so this will be one where if you don't do the graph, and you just say, well, the cube one's probably bigger, I'll just assume that one's bigger. And hey, if I get it wrong, I'll just change the sign. Well, that won't work on this one. It's going to have to be two integrals. So negative 3 to 0, y1 minus y2, plus 0 to 3, y2 minus y1. Because there's a different top and different top, different bottom for each little piece. All right, let's leave that because that's just a bunch of typing into the calculator at that point. Number 5. Find the region bounded by the graphs. Oh, lovely, we have 3 graphs. y1 is the parabola. y2, negative x. Okay, I know which one that is. And y equals 4x. I'll call that one y3. And we want the area bounded by those 3 graphs. So I guess our first job is to figure out what area we're talking about. So I think we're talking about that area. Like one of these pieces? Well, if it was that piece, that's only using y1 and y2.
Well, I'm saying you know where they go with that top with the curve above it?
Like up here, this little pie piece?
A little bit to the left, right?
This little pie piece?
Yeah.
I mean, it includes that, but we sort of want these 3 graphs to make the outer boundary of the region. And again, we have a top minus bottom issue here. By the way, I think we can, to save time, we'll say they intersect at 6. There's an intersection at 0 and an intersection at 4. But I've got a top minus bottom issue going on here. It might have been better if I'd have colored the. So y1 is the black one. y2 is the red one. And y3 is my blue one. So from negative 6 to something. So what's my first region going to be? It's going to take multiple regions. Negative 6 to what? To 0. And what's top minus bottom between negative 6 and 0? Which function is the upper function? From negative 6 to 0? y1 is the upper bound. And the bottom one is y3. And then from 0 to 4, who's the top guy? Like look at your area. Don't look at like y3 goes way up there, but from my area pieces, the top one is y1 again, and the bottom one is y2. And again, now you're ready to go put that in the calculator. So again, this unit is not almost no computation. It's more like visually, can you see what's going on? Last one. Again, the assignment will be 1 through, actually we'll omit 15 when we get there, and omit 14. Yeah, so your assignment will be 1 through 13. But we need to do number 6 in 2 minutes, which I think we can, oh no, 8:15, we're good then. Number 6, find the region bounded by x equals and y equal and x equals. So this is different. X equals and y equals. Well, even though I don't usually graph this way, one of them's got a cube in it, so a squared in it, so I'm pretty sure this is x1. And even though it's out of whack, the line would be x2. Now, it kind of gives you a hint here. Rather than integrating using x, use y, and you go right to left instead of top to bottom. If we did top minus bottom, we would have to do 2 different, well, that'd be really hard, because over here the top and the bottom would be the same curve. So that would be kind of unusual. So this is a weird one that we're gonna go left minus right, or right minus left, excuse me. That's kind of what you do. You're right. So the question was, can I just turn my paper? Sort of. You actually, I think you could, Connor, if you just switched all the x's and y's, I think you'd still get the right answer. I think you could do it that way. But I don't know that always works. So let's, for this one, we're going to integrate right minus left instead of top minus bottom. And our, the width of a rectangle, if that's our rectangle, the width of that rectangle is dy. So this is a little bit weird. So we're integrating dy. The rightmost one minus the leftmost one, that would sort of be the height of the rectangle. Still doing height and width. So the height of that rectangle, or I guess because of how it's situated, the length of the rectangle is the right function minus the left function. So that's x1 minus x2. And now my limits, since we're sort of taking y rectangles instead of x rectangles, my limits need to be y limits. So my limits need to go from -2 up to 1. Let's see. This one's a little harder to do in the calculator because you don't have x equals and you don't have x equals in the calculator. So 3 minus y squared minus y plus 1 dy. So math 9. Now I'm going to type this one in kind of manually here instead of using the variables. 3 minus y squared minus y plus 1 dy. And all of that, I get an area of 4.5. Connor, if you had switched all the x's and the y's, you'd end up with, you can do it the same thing here. You'd switch all the x's to y's, and you still get the same answer. And by the way, as far as integrating, even though your paper says this, in order to save a little bit of time, a lot of people will put x's in the calculator because it's easier to hit the x button. It's just one button. The y button, you got to do alpha y. It's minor, but again, this is the official answer. But when people put it in the calculator, a lot of times they just use x's because it's easier. All right, we're not going to do 7. Your assignment is 1 through 13. Try 13. I don't know that you'll be able to do it, but try 13. Get it set up if you can. Actually, let's make number 13 a set up but do not solve problem. That'll make it a lot easier when you get there. The boxes are just for graphs, and they don't give you the scale, so it's going to be kind of on you to, figure out on your calculator, well, what window do I need to look at to see everything? So maybe start big and work your way small. There's also a window like a zoom fit. It doesn't always work great though. If you go to zoom and scroll down to 0, zoom fit, it might work, it might not. And we'll go over some of those tomorrow.